So what are we talking about when we say toolroom spindle? This is anything like a Harrod grind-all or a Suburban tool spin fixture. Anything that rotates the part typically has a 5C collet or an adjustable V-block. That's the type of thing we're talking about. So this is the version that I've designed, and I'm trying to get something that's quite a bit more accurate than the standard one, hopefully down in the 5 millionths TIR range or better. So this is the construction of it. We're showing the bare unit here, and now you're seeing it with the 5C collet adapter bolted on the front. This outer ring has adjustment screws that will act like a buck chuck to be able to tweak in the TIR of a collet after it's in there. And the lock nut for the collet is in the back here. Here in cross section you can see how the nut bears only on the inner collet body, not on the spindle, because pressures on here with the collet tension would affect the preload on the bearings. This is all hardened A2 tool steel with the bearing races lapped directly on the material, and we're going to be using grade 5 balls, which are 5 millionths roundness and 10 millionths match in size for the entire lot. So there's a lot of balls in here to give elastic averaging, so all those roundnesses will elastically average out and should give better TIR than it would with a lot larger balls. Here we're showing a magnetic chuck mount where I have these eccentric pins and the pull studs that pull this back against the chuck blind. This is about a 4 3/4 inch chuck, and then I also have a 10-inch chuck that will mount on here with the same pin system, and there's 12 of these evenly spaced around here. You may be wondering why there's so many holes here, but in high precision applications the influence of the forces that the screw puts in the bolt holes will actually distort the shape of this. If there was only 3 holes on here, this would start to take a trilobular shape, and that would influence the accuracy of rotation since the races are directly on the shaft. So by putting multiple closely spaced smaller screws in, it distributes this out where the deformation starts to overlap, and this will be much more round and uniform both facially and radially than it would be with lesser screws. And you can see the outer bolt circles also have 12, as do the eccentric lock style. In this video I'm going to cover the general machining of the main components here, and other videos will cover some of the other aspects of the construction of the eccentric pins and some of the attachments. First we're going to take a look at machining the housing. Very simple part actually, very few details on here. Yes, there's a lot of tapped holes, but other than that the geometry is very elementary.
Here on the roll-in, getting ready to cut the spindle housing to size. It's already on size on the clamped direction, using the digital stop I made for the roll-in. Awesome. You guys definitely need to make one of these. Really, really handy.
Facing off the first surface of the block, using face mill, obviously it'll get flipped over and the other side done. Squaring one edge, they'll all get squared up. Putting a 3/4 hole in through the whole part so that I can dive in with my insert cutter, which doesn't end machine all the way. As you can see here, this lets me dive in the center and just use a pocket mill routine to rough out all this material. And we're doing this to both sides to remove the mass material. Then we'll go on the lathe and hit those parts from there. Now we're doing the central bore halfway through. There it is, both sides finished. We're going to grind the 2 large faces of both housings. We're doing 2 different sizes of these at the same time, and stoned the chuck, stoned the pieces, put them on, and these are going to get ground together. Grinding one side, we'll flip them and do the other side just the same, still leaving a grind allowance for after heat treat.
Now we're going to square up one edge in both directions at once. I have a SPI hardened magnetic V-block that I bought long ago, and this thing is really just probably one of the most useful grind tools that I have. It's extremely precise as is, and I have relapped the bottom once where it has worn just a little bit, but it's basically dead nut square in both directions. So by putting this on at a 45 degrees, have my little plastic protractor here, and taking my 5-inch distance of the first piece, and I'm saying, okay, I want to get this where the center of my grind stroke wheel center down here is roughly right there. That puts me where I'm the same crank and a little bit further. So I'm saying 5-inch, 2.5. I'm getting this lined up. That's the bottom of my crank, so that my directions both ways are the same. Just makes it nicer for grinding. Okay, now that that's on, a important note relative to using anything like this that's a reference, whether it's a precision square, a toolmaker's knee, whatever it is, you always want to support the center of gravity of the part you're putting on there on the chuck, so that by doing that you take all bending loads off of this, because now all the weight's being supported here at the center of gravity, so there's no moment loads like this pulling on this part. Everything deflects. It's just a matter of how much. So by doing this, I'm going to put this little steel chiclet here, 2.5 by 1 location, center of gravity of the part. Turn this on, wipe my V's. I take my part now, and I'm going to stone where this is going to sit on this first side. And now I'm going to put this in, get my on-off switch here, and I'm going to put this in. I'm going to put it in just with a little bit of magnetism on. I'll turn this on just a trifle, so that this is being held. Now what I'm going to do is I'm just going to tap this down. Now I'm sitting. Now I just want to make sure you understand the principle here. By putting a support at the center of gravity of this part, there are no longer any loads. If this was an angle block or whatever, and all I did was clamp it sitting in midair, now this weight is pulling down. It's putting a moment load on this, and it's deflecting it. Here I basically have not altered the accuracy of this block at all, because I've taken all moment loads off of it. So, important concept. We're going to grind this, and then we'll flip it and do it again. We'll have two sides perfectly perpendicular, two directions. Advantage of the V-block is we are doing two directions at once. I'm getting squareness to this face right here between these two faces, and I'm getting squareness here simultaneously. So that's the beauty of the V-block.
Now we're doing the other side perpendicular to the side we just ground. So we're resting on the ground face, putting it in, lining up, and then we will grind this face. And once this face is ground, then we can just put these two faces on the chuck and just grind parallel. We don't have to use the angle block anymore. But this gives us squareness in both directions very easily. Measuring the height. Remember, we're still leaving material for grind allowance on these sizes. Digital height gauge is really handy for that. Now we're moving on to drilling the tapped holes. We're spotting here. Not showing the entire pattern, just enough to get the idea. Now we're drilling a tapped hole for all these. And now we're drilling the counter hole for the thread relief. Now we're spotting the air purge holes down in that little lip. Have to be very careful about the spot drill not moving off. Now we're drilling the actual hole that will run into the hole you'll see in the next picture.
Just a little note here about cross drilling and threaded holes and things. This is really a place where some little flappy micro burrs can form. And if you think about the function of this spindle, ultra high precision TIR, and you're going to blow air through here as an air purge when necessary, any particle of metal that could dislodge and all of a sudden go through that gap, even though this is designed to be after the bearings, would be not a good idea. So that's why I'm taking a little diamond ball burr, as you'll see here, to do the deburring in the bottom. Here's one of those cheap diamond plated mandrels that I've turned the neck down on to be able to get in here and do the deburring you saw there. So right here, in here, I can put that ball burr in and sweep that until the edges get deburred, and do that to all the holes, because the same thing applies there. Any little burrs or anything that could break loose after heat treating would be problematic.
Doing the same holes on the other faces, spotting. This pattern matches the Renzetti pattern. This is the tapped holes. And now we're doing the counter drill hole, and you'll hear why we're doing that now. You'll notice that all of the holes that we put in these fixture parts that are hardened steel have a relief diameter here, which is really just a drill point. And that relief diameter is a little bit larger than the OD of the thread, in this case 1/4 So this diameter you see here is the tap drill, but this is counter drilled down through this about 1 or 1.5 pitches of the screw to make sure that this doesn't pop out from the loads that occur right on the edge of the part. Remember that as these tool steels get hardened, they get a little bit more brittle, and since the screw stretches in the process of applying tension, the heaviest loaded lead of the thread is right at the face. And the next picture is going to show you what happens when you don't do this to a hardened tool steel piece. As you can see on this piece, those broken out faces around the screw holes are from not putting that relief around the screws. So it's a very important thing on hardened parts.
I have the larger housing on the 6 jaw now. These were just roughed out with a insert mill, as you saw before. Now I'm going to finish turn these before heat treat. I'm going to be leaving 10,000ths on each surface to hard turn and grind and lap afterwards. So we're coming over here and I'm just double checking my TIR facial. This is just how I stuck it in the chuck, and we're running less than a half, which is plenty good enough, because this is, like we said, this is still somewhat rough. One thing to note when you're doing something like this, I'm going to be indicating this part in and indicating directly on the flats here. You want to line the flats up with your adjustment screws, or your buck chuck or set true chuck style adjustment screws, so that you have a direct relationship of the movements rather than having to jockey them around and not have a one-to-one. You can do it the other way, but it's just a lot more, makes life a lot more difficult. So now I'm going to set up to indicate on top here, and I like to get just a little bit in towards me from center so that I can use the cross slide to do the fine tuning, and you'll see technique wise what we do here. So I find that, so I can adjust now just by moving the compound in. I have a very fine adjust of getting on 0 without having to touch the indicator. So that is my 0 on my 2. I'm going to go to my opposite to my 4. Come in and see where it is. Wow, amazing. That's just the way it was on the chuck. Okay, that's a half high. On this side, we're about 1 low. See that? That should go down. And then I'll come crank up on my 3 side. Well, it's these numbers I'm referring to are the numbers of the actual adjuster screws. So I'm half low there, over here, and on here. So I want to release this a little bit. And remember, this is, as a matter of fact, that was just not even tight, so I'm just going to snug that one. Nudge my camera, and I'm going to jack this one a little bit snugger. And this doesn't need to be dead nuts because, like I said, we got 10 thousandths we're leaving on here, so that's plenty good enough for what we're doing. And for those who might not have seen it before, all my machines, I have a post here that is the same as the post on my magnetic base, and I have my fine adjust, captive fine adjust here. That's a flexure, so there's no joint slop or anything. This is really, really handy. If I mean, I do tons and tons of indicating, and putting a magnetic base on and off the machine is just silly if you do a lot of it. It just pays to have a post there ready to go. It doesn't interfere with anything, and it just saves a lot of time. And the people that have adopted this agree. It's just really, really handy. The bore, this side, the other side's already done. I'm just showing the operations on this side. I already flipped it once. Punch in my tool number and my target dimensions. Say 20 away for my last cut. Stay 5 away on my face. Climb up the face. I would normally use coolant. I'm just doing this so you can see what's going on. Okay. Come out here, go to my 0 size. This particular diameter will not be cut again. This is clearance. So will stay this way after heat treat. Okay, come into my actual finish, Z, which is leaving 10 thousandths on that base for hard turning and lapping. Okay, get off of that, come into my inner bore. Okay, come to size, which is 10 thousandths small, and then I will be ready to crank off the bore as I trail off here, so I don't need a big mark. There we go. Come out to our size. Run a little slower here. And we're going to run in here and do our so we don't have a stress riser in that corner. Got a full 30-second radius there. A2 isn't real notch sensitive anyhow. Little bright boy stick, get the fuzz off. Knock the corners. And we'll take a piece of bright boy and go down here into the corner and polish the radius so that is a nice smooth surface, so that no cracks or whatever we'll want to initiate there. There you have it. That's ready for heat treat. Now it'll be lather, rinse, repeat on the smaller 4-inch square version. Same tools, same procedure. Here's a big pile of A2 rounds for the spindles that we're going to knock down with the Tormach and the Harding. I'm going to tag team back and forth between these two. Using the old rotor brooch here with coolant fed in from the back and a pinch style 3/4 diameter boring bar holder. And taking the slug, I'll do half from this side, half from the other, and then I'll go around the Tormach and finish boring these. Here's inside the Tormach. I have 2 tool posts on at the moment, and just using this as a manual lathe basically with the conversational programming, which is really handy. So I set my compound at 24 degrees to machine the taper on the collet nose adapter for the toolmaker's spindle. Here I've got my indicator in. I'm using my adjustable chuck stops, and down here I'm checking the actual run out of those, make sure that they're still good from their last setting, and coming around and checking on each one, and then that's going to let me put my part in. I just bored the internal contour for the collet, and that's it there. Collet taper, relief, and then the undersized diameter here that'll get ground in the back for the 1.25" of the collet seat. There's the OD contour of the collet nose, the actual for the larger spindle collet nose.
We're doing the holes on the face of the actual spindle itself, spotting, doing the tap drill holes, doing the outer rim tap drill holes. Now we're doing the counter drill holes on those inner and outer. These are the spot drill for the cam lock positions. This is a regular drill that we're going in to do the main metal removal in the hole. Now it's a flat bottom drill that we're going in to clean up the bottom before we go in with an end mill and do a circular interpolation around there to actually finish the holes off. End mill has a corner radius on it to not cause a stress riser. Now we're spot drilling for the counter bored holes that are where the screws go in that actually hold the spindle together. This is the through hole for the bolts. It goes clean through the end cap. This is the end cap now, not the spindle. The back half of the spindle. Now we're counter boring with the end mill.
I need to phase the tapped holes on the far side of this part to be in between the holes that the two drills are in, or basically bisecting that line. So those two holes are actually one hole off of being on center, which bisects that angle. I'm just using a toolmaker's flat here instead of going over the surface plate, so a surface plate would do the same thing. While that's held in there, I'm just using 1-2-3 block to temporarily super glue a parallel on in that orientation. That will allow me to indicate on this edge, when I put it in the chuck, gently spin it around until I've got that indicated in true, and that will give me my alignment. I had the same situation on this one where I've already glued my piece on, and same thing where I needed to phase the holes in. Technically there's no need for the phasing, but it pays to always, if you can't think of a reason why they should be phased, it certainly doesn't hurt. So the extra little bit of time to phase them means that someday down the road when I decide to bolt something on both sides of this and say, oh darn, if I'd only lined those two things up, this would work, I'll think back to this moment and say, wise decision.
Shop milling the index grooves in, and then we'll do a profile cut. Soon as we remove the material with the chop milling. There it's doing the profile, and it's indexing its way around. It'll be 75 divisions on there, and this will be ground after heat treat.
So here's that setup with the parallel glued on. I've touched in the center and then moved off to each side, gently grabbed the chuck and tapped it around until I got to run true. So as we traverse here, we'll see that for a bolt pattern that's plenty close enough. And that's just a technique to be able to pick something up on another side that's temporary when you don't have access to it. I'm putting the radial holes in the main spindle that are for the eccentric actuating pins. So right through here you've got a 3/16 hole, 1/8 inch hole, and that supports both ends of the pin where it's eccentric in the middle, and that will pull down the posts that are mounted in the chuck as it goes down. So there's the setup. I have my 6-jaw chuck mounted on my Harding indexer set. Just a few details here. I've taken my Harding indexer and I've milled flats aligned with the spindle so I can grab it in the vise. I've also mounted a plate on the bottom semi-permanently that allows me to grab this vise, or the whole setup in the vise, sticking vertically. So instead of having to take things off the table and T-bolts and all that, I can literally just stick this vertically in the vise and grab it. Doesn't work that well in the Bridgeport because it doesn't have enough Z-travel, but over in my DPM I've got a ton of Z-travel, ridiculous amount, so I can put this vertically and actually drill things with plenty of room to spare. So when you put a part in something like this, there's quite a few alignments that need to take place here. Number one, I have to rotationally phase this pin in to be on center just by moving it in the chuck jaws. I don't have any fine adjust here. This is just an index pin style of indexer, so I have no means of phasing other than that adjustment. I also have to make sure that it facially runs true in the chuck. I have to adjust it. This is a buck style, adjustable chuck, set true, whatever you want to call it. So I have to make sure this runs true. And then I have to pick up center. So once I've got this running true diametrically, I can sweep this with an indicator and the spindle on both sides, just hitting on the tangents here, get on center so I know where my zero center is. Once I have that, I can move over, put a gauge pin in here, which I did, and indicate on each side of it by finding the high point, both vertical position of the probe and rotationally finding the low point on both sides to phase this in and gently tighten the chuck, get everything lined up. Then recheck the facial runout and recheck the TIR. Once that's all set, now I'm actually on the axis of this hole, and then I'll be able to just index my 12 as I go around putting the features in.
Spot drill on the outside. The actual drill for the outer hole, reaming the outer hole, spotting through down to the bottom of the other side of the hole, drilling the bottom side of the hole for the other smaller ream, the smaller ream, and there's a test fit with the eccentric pin.
There's a couple of the time-saving features I've mentioned before. Flats on the backing plate so you can grab your chuck backing plates directly in the vise, and the adjustable chuck stops. Just makes for a real easy way to get these things in and level and be able to come in and indicate in with the indicator to get on zero.
Here we're doing the counter bores in the collet nose, starting out with just a straight plunge with an end mill. Now we're using the same end mill, but we're doing a circular interpolation in 3 steps to open the hole size up. Then a spot drill down at the bottom to guide the through hole drill that we'll do right here. Hard turning a woodruff cutter neck down for clearance.
Here's the setup with the Harding dividing head. I have a 17 hole plate on here. The sector set for 4 holes since this is a 4-to-1 reduction. I have the 2 degrees tilt of the entire spindle set on the tilt. And right now I'm touching off on the top of the chamfer because I have a dimension on the drawing of how far down I go to get the bottom face of the cutter splitting the center line of the part.
Now we're just milling through each face, and it's cutting the opposite face on one side than the other. It's kind of confusing because the face of the cutter is right on the center line. And here we're tapping in the position of the next part. Here's a slideshow of the spindle pieces assembled with 1, 2, 3 blocks and plates, large 10-inch chuck on the larger spindle, then the smaller spindle mounted on the magnetic chuck. These are just some examples of things that could be assembled with the system. This is all pre-heat treat, testing the parts, make sure everything fits. And